Welcome to this coding walkthrough. In this session, we'll tackle LeetCode problem number 1850, minimum adjacent swaps to reach the kth smallest number. This problem challenges us to determine the minimum number of adjacent swaps needed to transform a given number into its kth smallest permutation. Let's dive in and explore the solution step by step. In this problem, you are tasked with finding the minimum number of adjacent swaps needed to transform a given string number into its kth smallest permutation. Here, the string number represents a large integer composed of digits from 0 to 9, and it has no leading zeros. The integer k specifies the permutation order we are trying to reach, based on 1-based indexing. For example, the first permutation is simply the original number, the second permutation is the next smallest arrangement of its digits, and so on. You're required to calculate how many swaps of neighboring digits are necessary to achieve exactly the kth permutation. The output will be a single integer representing this minimum number of swaps. This is a combinatorial problem that involves understanding permutations and optimizing the process of transforming one arrangement of digits into another. Let's look at an example to clarify the task further. Consider the input where number is 548, 935, 5142 and k is 4. The goal is to find the fourth smallest permutation of the digits in number. Listing the permutations in ascending order, you get, the first smallest permutation is 548, 935, 5142, the second is 548, 935, 5412, the third is 548, 935, 5421, and the fourth is 548, 953, 1452. Now, to transform the original string 548, 935, 5142 into 548, 953, 1452, the minimum number of adjacent swaps required is 7. Therefore, the output for this example is 7. This demonstrates how the problem involves both generating the kth permutation and calculating the minimum swaps needed to achieve it. Let's examine another example to further solidify our understanding. In the next example, the input is number equal to 11,112 and k equal to 4. The permutations of 11,112 in ascending order are, the first smallest is 11,112, the second is 11,121, the third is 11,211, and the fourth is 12,111. To transform 11,112 into 12,111, we need to perform 4 adjacent swaps. Thus, the output is 4. This example highlights how the process becomes simpler when there are repeated digits, as the number of unique permutations is reduced. Now, consider a case where no swaps are needed. For the input number equal to 00123 and k equal to 1, the task is to find the first smallest permutation. Since the input number itself is already the first smallest permutation, no swaps are needed. Therefore, the output is 0. Finally, let's review the constraints. The length of number can range from 2 to 1000 digits, and k can go up to 1000, so the problem must be solved efficiently even for large inputs. Test cases may include small inputs, cases with all identical digits, scenarios where the number is already the kth permutation, and large-scale cases to test performance. These constraints and edge cases are critical to consider when designing your solution. To approach the problem of finding the minimum adjacent swaps to reach the kth smallest permutation of a number, we need to combine our understanding of permutations with strategies for minimizing swap operations. The first approach we consider is the brute force method. Here, the intuition is straightforward. We generate all possible permutations of the given number, sort them lexicographically, and identify the kth smallest permutation from this sorted list. Once we have the target permutation, we calculate the minimum adjacent swaps required to transform the original number into this kth permutation. However, the complexity of this approach is a significant drawback. Generating all permutations grows factorially with the length of the number, and sorting them further adds computational overhead. While it's conceptually simple, this method quickly becomes impractical for larger input sizes due to the sheer number of permutations involved. A more efficient alternative involves directly computing the kth smallest permutation without generating all permutations. This is achieved using the next permutation algorithm, which allows us to iteratively generate permutations in lexicographical order. By repeating this process k times, we can directly obtain the kth permutation. Once we have the target permutation, the next step is to calculate the minimum adjacent swaps needed to transform the original number into this new arrangement. To do this, we align the digits of the original number to match the target permutation, moving mismatched digits to their correct positions using adjacent swaps. While this approach avoids the factorial complexity of generating all permutations, the swap calculation still involves nested loops, leading to an O(n)² complexity. Overall, this method is significantly faster than brute force and is well suited for larger inputs, though the swap calculation step could still be optimized. Another strategy builds on the optimized approach by combining permutation generation and swap calculation into a single process. This greedy method focuses on transforming the original number into the kth permutation while minimizing swaps at each step. After computing the kth permutation using the next permutation algorithm, we align the digits of the original number to the target permutation directly, ensuring that redundant operations are avoided. This reduces some of the overhead seen in the optimized approach, though the complexity remains k times n plus n squared. In practice, this greedy approach may offer slightly better performance due to its streamlined operations. However, it shares the same limitations as the optimized method, particularly in the O(n)² swap calculation step. Ultimately, while the greedy method is conceptually simpler, it doesn't offer a significant advantage in terms of asymptotic complexity. The key to solving this problem efficiently lies in leveraging the next permutation algorithm, which allows us to directly find the kth smallest permutation without generating all permutations. This reduces the problem to aligning two strings, the original number and the target permutation. By simulating this transformation, we can calculate the minimum adjacent swaps in O(n)² time. The brute force approach is clearly infeasible for larger inputs due to its factorial complexity, highlighting the necessity of these optimizations. The chosen strategy, optimized permutation generation combined with swap calculation, strikes a balance between efficiency and clarity. While its k times n plus n² complexity is not the absolute fastest, it is manageable for typical constraints and avoids the additional complexity of advanced data structures. However, there is room for further optimization. For example, reducing the swap calculation to O(n)log en using data structures like Fenwick trees could improve performance, though this would come at the cost of increased implementation complexity. Overall, this approach is practical, efficient, and well suited to the problem's constraints. This problem challenges us to transform a given string number into its kth smallest lexicographical permutation using the minimum number of adjacent swaps. To solve this efficiently, we break the process into two main steps. First, we generate the kth smallest permutation. This involves repeatedly applying the next permutation algorithm, which operates by identifying the rightmost character that can be increased, swapping it with the smallest valid character to its right, and then reversing the sequence following the pivot to ensure the result is in the smallest lexicographical order. This gives us the target string we need to reach. Once we have the kth permutation, the next step will focus on transforming the original string into this target using the fewest adjacent swaps possible. Now that we have the kth permutation, the next step is to calculate the minimum number of adjacent swaps required to transform the original string into this target. This is achieved using a two-pointer approach. Starting with the original string and the target string, we align their characters one by one. For each mismatch at index I, we locate the corresponding character from the target string in the original string and move it to the correct position using adjacent swaps. Each swap brings the strings closer to alignment. By iterating through the entire string and keeping track of the swaps we make, we can ensure that the transformation is completed with minimal effort. This approach avoids unnecessary operations and adheres to the problem's constraints. The use of the next permutation algorithm is crucial here, as it allows us to directly generate the required permutation without exploring all possibilities, and the two-pointer strategy ensures that swaps are optimized for correctness and efficiency. To implement this approach effectively, we rely on specific data structures and analyze the computational complexity. The string representation of both the original and target permutations allows for straightforward character manipulation. The two-pointer technique enables efficient traversal and alignment of the strings. In terms of complexity, generating the kth permutation involves O(n)k operations, where n is the length of the string, as we may iterate through the string up to k times. Calculating the minimum swaps can take up to n squared, in the worst case, as adjacent swaps might involve shifting characters multiple times. Combining these, the overall complexity is n times k plus n squared. On the other hand, space complexity is limited to n, as we only store the strings and a few auxiliary variables. Special cases include scenarios where no swaps are needed, such as when k equals 1 or when all characters are identical. Additionally, the algorithm handles large values of k efficiently by leveraging the next permutation strategy. Let's apply the algorithm to an example. Suppose we are given the string number equals 548935 and k equals 4. First, we generate the kth permutation. Starting with the original string, the first permutation is 549358, followed by 549385, 549538, and finally, the fourth permutation, 549583. This becomes our target string. Next, we calculate the minimum swaps required. To align the first character, we swap 5 with 4. We then move 4 into position using adjacent swaps. This process continues for all characters until the original string matches the target. By counting each swap, we find that the minimum number of adjacent swaps required is 4. This example demonstrates how the algorithm efficiently achieves the transformation, adhering to the constraints and optimizing the number of moves. Here, we start by importing the ILIS function from the itertools module and defining our solution class. Within the class, the getMinSwaps method calculates the minimum number of adjacent swaps needed to transform a given number into the kth smallest permutation of itself. The first step is defining a helper function called next_permutation. This function finds the next lexicographical permutation of a string. To do so, we convert the string into a list for easy manipulation and calculate its length. Starting from the rightmost side, we search for the first decreasing element. This is done using a while loop, which continues as long as the current element is greater than or equal to the next one. If no such element is found, meaning the sequence is already in descending order, we simply reverse the entire string and return it since it's the last permutation possible. Otherwise, we move forward to identify the next greater element on the right to swap with our selected decreasing element. After swapping, we reverse the portion of the sequence to the right of the swapped position, ensuring the result is the next permutation in lexicographical order. The helper function concludes by returning the newly formed permutation as a string. With this in place, we proceed to generate the kth permutation from the input number. Starting with the input string number, we repeatedly call next_permutation k times to arrive at our target permutation. Once we have the target, the next step is to calculate the minimum number of adjacent swaps required to transform the original number into this target. We convert both number and target into lists to allow in-place modifications. Using a for loop, we iterate through each position in number. If the current elements in number and target differ, we locate the position in number where the target element appears, using a nested while loop. Once found, we perform adjacent swaps to bring this element to the correct position, incrementing the swap count after each operation. This process ensures that we gradually transform number into target with the minimum number of swaps. Finally, the total swap count is returned as the result of the method. Here, we begin by defining a method getMinSwaps that calculates the minimum adjacent swaps needed to transform a string number into its kth lexicographical permutation. First, we generate the target permutation by calling the helper method next_permutation k times on the input string. This gives us the desired kth permutation. Next, we compare the characters of the original string number and the target permutation to determine how many adjacent swaps are required to transform one into the other. We convert both strings into character arrays, number array and target array, for easier manipulation. Then, we iterate through number array. Whenever we find a mismatch between number array and target array, we locate the position of the target character in number array and repeatedly swap adjacent elements to move it to the correct position, incrementing the swaps counter for each adjustment. The swapping process continues until the mismatch is resolved, ensuring that the arrays align step by step. Once all mismatches are corrected, the total number of swaps is returned. Now, the next permutation method is designed to generate the next lexicographical permutation of a given string. It begins by converting the string into a character array for easier manipulation. The goal is to identify the first decreasing element from the right, which determines the point where the next permutation differs. If no such element exists, it means the string is already the largest permutation, and we simply reverse the entire array to reset it to the smallest permutation. Otherwise, we locate the smallest element to the right of this position that is greater than the identified element. Once the appropriate element is found, we swap it with the identified element to create a slight ordering increase. After the swap, the portion of the array to the right of the swapped position is reversed to ensure it is in its lowest possible order, completing the transition to the next lexicographical permutation. The modified array is then converted back into a string and returned. Lastly, the helper method reverse is used to reverse a segment of the character array between specified indices. It swaps elements at the start and end of the segment, progressively moving inward until the entire segment is reversed. This utility function ensures that the portion of the array is reordered efficiently, forming a crucial part of the next permutation logic. In this example, we start with the number 548-935-5142 and are tasked with finding the fourth lexicographical permutation of this number. Once we find that permutation, we will calculate the minimum number of adjacent swaps required to transform the original number into the target permutation. First, to find the fourth permutation, we use the helper function next_permutation. This function allows us to compute sequentially the next lexicographical permutation. After 4 iterations, we arrive at 548-953-1425, which is our target permutation. Now, to calculate the minimum adjacent swaps, we compare the original number and the target permutation. Representing both as arrays, we initialize a swap counter to 0 and begin the process of aligning the two arrays to match the target arrangement. To begin the transformation process, we compare the array's element by element. At index 4, the original number has a 3, but the target number has a 5. To correct this, we perform adjacent swaps until the 5 reaches the correct position. Swapping number 5 with number 4 updates the array and increments the swap count to 1. Next, at index 5, the numbers already match, so no swaps are required. Moving to index 6, the original number has a 5, but the target has a 1. Here, we swap number 7 with number 6 to bring the 1 into position, resulting in 2 swaps so far. This process of comparing, identifying mismatches, and making swaps continues until the entire array matches the target. By the end, we calculate a total of 7 swaps to transform the original number into the target permutation. The output for this example is therefore 7. In this simpler example, the input number is 12,345, and we need to find the first lexicographical permutation, which is just the next permutation of the number. Using the next_permutation function, we find that the target permutation is 12,354. To calculate the minimum adjacent swaps required, we compare the original array 1, 2, 3, 4, 5 with the target array 1, 2, 3, 5, 4. At index 3, the original number has a 4, but the target number has a 5. To fix this, we perform one adjacent swap between number 4 and number 3, which updates the array to 1, 2, 3, 5, 4. This single swap brings the original number into alignment with the target permutation. The total number of swaps required is 1, and the output is therefore 1. For the third example, the input number is 11,112, and we are tasked with finding the second lexicographical permutation. Using the next_permutation function, the first permutation is 11,121, and the second permutation is 11,211, which becomes our target. Now, to calculate the minimum adjacent swaps, we compare the original array 1, 1, 1, 1, 2 with the target array 1, 1, 2, 1, 1. At index 2, the original number has a 1, but the target number has a 2. To fix this, we perform 2 adjacent swaps. First, we swap number 3 with number 2, and then we swap number 4 with number 3. These 2 swaps bring the 2 into its correct position, and the arrays now match. The total number of swaps required is 2, and the output for this example is therefore 2. To analyze the time complexity, we break the solution into two main steps, generating the kth smallest permutation and calculating the minimum adjacent swaps. First, let's consider generating the kth permutation. This involves using the next underscore permutation function, which we call k times. Within each invocation of next underscore permutation, we perform three operations. Finding the first decreasing element from the right takes O, n, finding the next greater element on the right also takes O, n, in the worst case, and reversing the suffix requires O, n, as well. Together, each call to next underscore permutation has a time complexity of O, n. Since we repeat this process k times to compute the kth permutation, the total time complexity for this step becomes O, k asterisk n. Now let's discuss the time complexity of calculating the minimum adjacent swaps. In this step, we iterate through the number string, which has a length of n, and for each character, if it doesn't match the corresponding character in the target string, we perform a linear scan to find the index of the matching character. This linear scan can take O, n, in the worst case. Once the matching character is found, we perform adjacent swaps to move it to the correct position, which can involve up to O, n, swaps per mismatch. In the worst case, this process is repeated for all n characters of the string, leading to a time complexity of O, n squared, for this step. Adding the complexities of both steps together, the total time complexity of the algorithm becomes O, k asterisk n, plus O, n squared. The dominant term depends on the values of k and n. If k is very large, such as when k is equal to or greater than n, O, k asterisk n, dominates. Otherwise, O, n squared, becomes the primary contributor. For the space complexity, we again analyze both steps. In the first step, generating the kth permutation involves using the next underscore permutation function, which converts the string into a list for manipulation. This requires O, n, space. Additionally, reversing the suffix also temporarily uses O, n, memory. Thus, the space complexity for this step is O, n. In the second step, calculating the minimum adjacent swaps involves modifying the number list in place. Since no additional data structures are used apart from the input and target strings, this step also has a space complexity of O, n. Combining these two, the overall space complexity of the algorithm is O, n, as the memory usage is dominated by the storage of the input string and intermediate lists. To better understand the efficiency of this algorithm, let's compare it to a naive approach. A brute force method would generate all possible n permutations of the string, sort them, and then find the kth smallest permutation. This would require O, n asterisk n time, which is computationally infeasible for larger n due to the factorial growth. In contrast, the optimized approach directly computes the kth permutation in O, k asterisk n time using the next underscore permutation function. Additionally, instead of comparing all permutations, it calculates the minimum swaps in O, n squared, time, making it far more efficient than the brute force method. This optimization allows the algorithm to handle significantly larger inputs while maintaining reasonable performance. Finally, let's analyze the best, average, and worst case scenarios for this algorithm. In the best case, if k equals 1, meaning only one permutation is generated, and the number string already matches the target, the swaps are minimal. Here, the time complexity reduces to O, n, for the swaps, resulting in a total complexity of O, k asterisk n, plus O, n, which simplifies to O, n. In the average case, for typical values of k and n, both steps contribute significantly to the overall complexity, leading to O, k asterisk n, plus O, n squared. In the worst case, if k is very large, such as close to n, or the string requires many swaps, the time complexity is dominated by O, k asterisk n, plus O, n squared. Mathematically, this is valid because the next underscore permutation function is called k times, each with an O, n, cost, giving O, k asterisk n. Similarly, the adjacent swaps involve nested iterations, with up to n iterations for mismatches and n swaps per mismatch, resulting in O, n squared. Together, the total complexity of O, k asterisk n, plus O, n squared, accurately represents the algorithm's behavior. One common mistake when working with this problem is misunderstanding how permutations are ordered lexicographically. The kth smallest permutation is not random, it follows a strict sequence based on this ordering. If you're unclear about this, your outputs might be incorrect, so take time to review the concept. Next, avoid inefficient swapping algorithms. A brute force approach that generates all permutations and sorts them can lead to time limit exceeded errors, especially when n is larger than 10 due to the factorial growth of permutations. Instead, leverage the next permutation algorithm, which is much more efficient. Additionally, ensure your logic accounts for adjacent swaps only. Some solutions mistakenly allow non-adjacent swaps, which violates the problem's constraints. Finally, always test edge cases thoroughly. For instance, if the input number is already the kth permutation, no swaps are needed. Similarly, when k equals 1, the result is simply the original string, so these scenarios need special handling. When the input number contains duplicate digits, it adds another layer of complexity to the next permutation step. If not handled carefully, you might end up generating invalid results or mishandling indices. Now, let's break the problem into simpler components. First, you need to generate the kth smallest permutation, which can be done efficiently using the next permutation algorithm. Second, you calculate the minimum number of adjacent swaps required to transform the current string into the target permutation. By approaching it this way, you simplify your thought process and implementation. The minimum swaps are determined by identifying positional mismatches between the current string and the target permutation. A two-pointer strategy is particularly useful here to reduce the number of operations. Lastly, interviewers often focus on whether you truly understand lexicographical order and whether your solution is optimized. So, be prepared to explain why your approach is efficient and how you've accounted for edge cases. This problem shares similarities with several others that you can practice to deepen your understanding. For instance, LeetCode problem 31, next permutation, focuses on finding the next lexicographically larger permutation, which is a core part of this problem. Problem 1202, smallest string with swaps, involves forming the smallest string after performing a series of swaps, which is conceptually related to minimizing transformations. Problem 1647, minimum deletions to make character frequencies unique, also revolves around optimizing operations on strings, though here the focus is on deletions. Lastly, problem 1847, closest room, while not directly about permutations, emphasizes careful constraint handling to optimize solutions, a skill that can be applied universally. Practicing these problems will help you better understand the patterns and techniques relevant to solving transformation-based questions like this one. There are several approaches to solving this problem, each with its own trade-offs. The brute force method involves generating all permutations, sorting them, and finding the kth permutation. Once that's done, you calculate the swaps needed. However, this approach is extremely inefficient, with a time complexity of O(n), and should be avoided for large inputs. A more practical solution is to use the next permutation algorithm iteratively k times to find the kth smallest permutation. After that, you calculate the swaps required to transform the current string into the target. While this method is significantly faster, with a complexity of k*n for generating permutations and n² for swaps, it might still be slow when k is large. For another alternative, you can use a BFS approach, which explores all possible adjacent swaps to reach the target permutation with minimal swaps. BFS ensures optimal results in terms of swaps but can be memory intensive for large inputs. The key takeaways here are to prioritize efficiency by breaking the problem into smaller subproblems, carefully handle edge cases like duplicates, and practice related problems to strengthen your understanding of permutations and transformations. Great job following along. To summarize, we broke down the problem step by step, identified the key concepts, and implemented an efficient solution. Remember, mastering problems like this can sharpen your problem-solving skills and boost your confidence. Thanks again for tuning in, and we'll see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!